Dear students, good morning to all. We will learn about virtual displacement, virtual work, principle of virtual work, and D'Alembert principle. First, we are going to discuss about the virtual displacement. Consider a system of particles in equilibrium. The total force on the every particle must be 0. Fi is equal to 0. Suppose this is the ith particle, will be ith particle. In this case, the force acting in that direction is 10, and the direction is 10. So the total force is 0. Now, before we are going to discuss the virtual displacement, we will learn about the work done by a force. If a rigid body is subjected to a force F which causes an infinitesimal displacement ds, then the work done by U, the force is doing the displacement F is given by U is equal to F cos theta into ds, where theta is the angle between the direction of force and the direction of displacement. Thus, we conclude that the work done by a force during the infinitesimal displacement is equal to the product of the displacement and the component of force in the direction of displacement. When a system of forces acting on a rigid body in equilibrium and the displacement of the body is 0, then no work is possible. But imaginary infinitesimal displacement is assumed to be given the body in equilibrium. Such displacement is called virtual displacement. For ith particle, the virtual work done can be written as Fi del Ri is equal to 0. For all the particles, virtual work done can be written as summation Fi. A means A stands for applied forces. Summation Fi, this is the force due to constraint. Del Ri is equal to 0. Now, here assume that the force due to constraint is 0. So, summation Fi A del Ri is equal to 0. Therefore, the virtual work is the work which is done on this system only by the applied forces. This is the principle of virtual work. So, the principle of virtual work applies only for statistical equilibrium. Now, we will see about the D'Alembert's principle. This principle states that for any body, the algebraic sum of externally applied forces and the forces resisting motion in any given direction is 0. If we have a dynamical system, for each particle, the rate of change of momentum is equal to Pi dot is equal to the net force on the particle Fi. We had already done that this force can be split into two parts. The one is applied force and the other one is constraint force. The one is applied force and the other one is constraint force. So this can be written as Pi dot is equal to Fi. Fi can be written as Fi applied force plus constraint force. This is constraint force. Now we will multiply by both sides with virtual displacement. This equation becomes summation I Pi dot del Ri is equal to summation I Fi. A stands for applied force plus forces of constraint into del R, and the sum taken over all the particles. As we know that the principle of virtual work, that the total work done by the constraint force is 0. So which implies that summation I Fi A minus Pi dot and del Ri vector is equal to 0. We know that all the virtual displacements for each particle, which is del Ri, they are not independent of each other. So I can't simply write this bracket becomes 0. So the D'Alembert principle becomes summation I Fi A minus Pi dot and del Ri is equal to 0 is known as the D'Alembert principle.